Hi, um, good morning. Um, this is a video for Chapter 5. In Chapter 4, we talked about um, crystal defects. One of the primary ones are impurities. And in Chapter 5, we'll talk about diffusion, which is one of the main mechanisms for introducing those impurities, especially in controlled amounts. So I'm going to switch over to picture-in-picture and share the notes for Chapter 5. Okay. So here we're talking about diffusion. So what do we mean by diffusion? Well, in this sense, right, you can have diffusion in any fluid. Gas diffuses, contaminants diffuse in a liquid. But here, since we're talking about materials processing, we're interested in diffusion in the solid phase, mass transfer in the solid phase. And just like all diffusion, here we're looking at movement of mass from high to low concentration. Diffusion occurs through random events, and so generally you get the production of disorder from order. To use this interface here between copper and nickel as an example, at the beginning you may have solid copper in contact with solid nickel, and at the interface, right, you have random interchange of copper and nickel atoms, and that interface becomes blurred, right, as randomly over time nickel atoms will move into the copper and copper atoms will move into the nickel. And if we remember back to Chapter 4, where we talked about solid solubility, right, copper and nickel are 100% soluble, and so they have similar sizes, similar electronegativity, similar valence, and so they very readily take the place of one another, and you get this movement of copper and nickel. And over time, the order that was here at the beginning, where you have a sharp interface, right, is lost, and as you have diffusion of one into the other. Of course, self-diffusion also occurs, right? Let's not think that only copper and nickel atoms will move into one another, right? You've got nickel atoms moving within nickel and copper atoms moving within copper. But it's more difficult to observe. Studies have been done to characterize self-diffusion, and these studies are typically done using different isotopes of the same element. So you can track the movement of a particular isotope within a material and characterize the self-diffusion. Okay, so what mechanism does diffusion happen under? Well, we're talking about is mass transfer, right? So we have movement of atoms within a material. And if we think back to our crystal structure, right, we remember that especially in metallic materials, the atoms are already very tightly packed, right? And so there's not very much space for them to move. And so that space needs to be created first before we can get atom movement and diffusion. And so there's typically two ways of finding any space with which to diffuse through. The first is via a vacancy. So one of the zero-dimensional defects, in addition to an impurity, is a vacancy, where we have a lattice position with no atom on it. And that provides an open space for an adjacent atom to move into, right? Which can provide a mechanism for an impurity to diffuse through a material. However, this is dependent upon the formation of this vacancy. So when we think about this process occurring and proceeding, you can kind of think about two activation energies. The first is the one required to create the vacancy in the first place, right? And if you think back to the chapter 4 material, there was an equation, right, that described the activation energy, or described the number of vacancies in terms of the activation energy and the temperature of the system. And then you need kind of a second process where once the vacancy is formed, right, there's an activation energy required to push apart these adjacent atoms. In this figure, it doesn't really look like they need to be pushed apart, but in general, they're going to be touching. So you need to push these apart to move into that vacancy, right? So there's kind of a two-step process with two separate activation energies, and this vacancy is required. So that's a vacancy diffusion. You also have interstitial diffusion, and that is, just like it sounds, movement of an atom from one interstitial space to the next. And here, you don't need the creation of a vacancy, because most of the interstitials are empty. If we remember, again, back to the previous lecture, for an example like carbon in iron to create steel, the maximum solubility is somewhere about 2%. So the vast majority of these interstitials are empty. And so more often than not, it will have an open interstitial to move into. So there's not the same requirement to create that space like there is with the vacancy diffusion. However, there is an activation energy required because these atoms are generally touching, and you need to push apart those atoms and increase their energy in order for that atom to sneak through into an adjacent vacancy. And so when you're considering the relative rates of diffusion for these two different mechanisms, the two things to think about are, okay, how big is the atom that's trying to move through the material? And how likely is it to have an open space to move into? And so on both of these accounts, right, you will see that interstitial diffusion is generally much faster, right, because there's only that one activation energy that needs to be overcome, because there's always an adjacent space. There's no need to create one. And the atoms are much smaller, so they can move through the material much easier. Later in this set of notes, we'll see a table where we can look at some numbers that compare vacancy versus interstitial diffusion rates. Okay, so mathematically, how do we think about diffusion? How do we represent it? And there's two general cases: steady state and non-steady state. So steady state is the more simple version. It's probably the less frequent or case. But here, and I guess in all diffusion, we're talking about diffusion rates, right? So this is a rate-dependent thing. You could get the same amount of diffusion at a lower rate just by waiting longer, right? And we characterize diffusion in terms of mass flux. So a flux is would be the mass per time over a certain area, would give us the flux of diffusing species. And steady-state diffusion exists anywhere where the concentrations on either side of some diffusion barrier are constant. So I like to think about an example that comes to mind here is like a helium balloon. So when you're a kid, you get a helium balloon. It's got a high concentration of helium on the inside, low concentration on the outside, and over time, what starts as a nice full floating balloon will eventually turn into kind of a saggy rubber, sad-looking balloon that eventually doesn't even float. And that's because the helium, over time, is diffusing through that balloon and escaping into the outer atmosphere, right? And so you'd expect that the rate would be relatively constant, because even though we're losing helium in the inside, right, the concentration is constant, right? And as it's moving into the outside, you're not increasing appreciably the concentration of helium on the outside, and so the outside concentration is staying the same, and so you have a constant rate, steady state diffusion through that barrier, and a constant or a decreasing concentration within the barrier of your diffusing species. This is also why if you ever got one of those shiny mylar balloons instead of a rubber balloon, right, it maintains its shape much longer because the mylar presents a higher, has a lower diffusivity of helium than, say, a rubber balloon. And the steady state diffusion is represented by Fick's first law. So here we're looking at the flux of diffusion, right? So mass per time per area being negative, meaning that it's going down concentration gradient. And it's dependent upon the magnitude of that gradient, right? So if I have a higher concentration on one side, I'm going to drive more diffusion across that barrier, and also this d constant, which we call the diffusivity, and that describes how easily the species that we are considering are diffusing through that potential or that diffusion barrier. Steady state is conceptually more simple, but it's not as commonly encountered as non-steady state diffusion. So in non-steady state diffusion, what we are talking about is a concentration profile that is changing with time. Right? Now here we're assuming, kind of implicitly, that our diffusivity does not vary with concentration. This is not strictly true. You can imagine a scenario where the concentration of your diffusion species gets so high that they start to interact with one another. But generally, we're going to consider situations where we're diffusing an impurity into a material, and that concentration is low enough that it's not interacting with each other to the point where that decreases its ability to diffuse through the material. And for non-steady state diffusion, right, at long times or short distances, you reduce to Fick's law. So if I look at this figure here, I can kind of qualitatively get a sense of this, right, where at short times, say T1, or thin sections. So if I were to cut the material here, right, I would see that it approximates that linear concentration gradient that I saw in my steady state diffusion. Or if I go to really long times, right, I approximate that linear concentration gradient through my material. But for shorter times, right, I have this exponential decreasing concentration of my diffusive species into the material. And Fick's law, or non-steady state diffusion, is described by what we call Fick's second law. And that is where we have a changing concentration with time that is dependent upon the second derivative of concentration in space times the same diffusivity. So we have a curvature of our concentration gradient that is changing with time. And the solution to Fick's second law is dependent upon what boundary conditions we impose. And so you have a solution, an expression that is dependent upon those boundary conditions, and you can look up that solution for various different scenarios. I think Callister actually gives a reference for where you might find those. But in this course, right, we're going to make use of a common one, and that is where you have boundary conditions where you're assuming a constant surface concentration. This is what you would find in the examples in this course, where we'd say, carburizing steel, diffusing carbon into the surface of a steel part to harden it, or diffusing impurity atoms into a silicon crystal to create N and P-type materials. Right? Both of these cases, we have relatively thick substrates where we're not diffusing all the way through, and also constant surface concentrations where we're not diffusing enough of the material into our part to change the surface concentration. And so under these assumptions, and assuming a few things, that we have an initial uniform concentration, defining the surface as x equals 0, and t equals 0 is when we start the diffusion, right? We develop this expression here that incorporates our initial concentration, our surface concentration, our depth, our diffusivity, the time, and includes this error function. And for the purposes of this class, right, the error function, we have tabulated values that allow you to evaluate and kind of invert this error function in order to solve for x or time or whatever it is you're looking for in your particular problem, and we'll do an example of this here at the end of this set of notes. And so what you end up with are concentration curves that look something like this, where you have a base concentration, usually, of whatever your impurity is, and you have a surface concentration. So the assumptions of your problem, right, this doesn't change because you're not exhausting the material at the surface. And you have this semi-infinite solid, so eventually you will reach a deep enough depth where it's the extent of the diffusing species, right? And you've got this concentration curve in the interim, and as you go longer in time, right, you're diffusing more and more species into the material, and so this curve is going to stretch deeper and deeper and become more shallow over time as you're diffusing more material into your, or more impurities into your material. And one of the driving factors for how fast you diffuse into the material is this D factor, this diffusivity, right? And we can represent it more fully with this expression here, where we include a constant times this exponential that should look familiar. We saw this in the last set of notes based looking at the vacancy formation, where we have this activation energy, which corresponds to how much energy it takes to, say, push apart the atoms of the crystal in order for the diffusing species to move through. And then we have temperature. And this diffusion coefficient here, or the D naught and the D, will differ depending upon what our diffusion scenario is. What we have, what element is diffusing, what the substrate is it's diffusing in, how is it diffusing, what's the temperature. And so to illustrate some of these differences in diffusion coefficient, I pulled this table from Callister, and it highlights a couple of these differences that I want to point out. The first, and this is something I alluded to earlier in this lecture, is the difference between vacancy and interstitial diffusion, right? So here we have our host metal, ferrite and austenite, right? So this would be alpha phase iron, which is BCC crystal structure, and gamma phase iron, which is austenite, which is FCC structure. And we've got iron diffusing in both of these crystal structures versus carbon diffusing in both of these crystal structures, right? And so if we come here and we look at the same situation, so iron versus carbon, iron has an activation energy of 250 versus only 80 for carbon, right? So it takes a lot more energy for that vacancy diffusion. And if we remember, we have to create the vacancy, and then we have to move into it, right? Which is kind of two separate activation energies which combine. We have a much higher activation energy than just the interstitial alone. And also remember, we have a much larger atom when we're trying to diffuse iron through the crystal structure than with carbon. And so these higher activation energies come over here, and you look at the actual calculated value for our D values, and you'd see that at the same temperature, the diffusivity for iron in alpha carbon is like 9 orders of magnitude lower than carbon in alpha iron, right? And so the mechanism has a huge difference, right? The other thing here is you would have the same species in 2 different phases, right? So if we would compare alpha iron versus gamma iron, right? Ferrite versus austenite, that's BCC versus FCC crystal structure, right? So think back to crystal lesson. What's the atomic packing factor of FCC? 0.74. And the atomic packing factor of BCC is 0.68. So in FCC, the atoms are packed in a lot more closely, right? There's less empty space in the crystal structure. And so if we compare the same temperature, so that would be 900 here and 900 here, right? We get about 2 orders of magnitude difference for the same element in this, or the same diffusing species in the same element, just based on what the crystal structure is. Okay, so more open crystal structures are going to have a higher diffusivity because there's more open space for those elements to be, those atoms to be diffusing through. And then lastly, I'll point out the temperature dependence. Right. So in all of these cases, we have an exponential dependence, and we have temperature here. And so in every case, right, if you want to increase the diffusion rate, the best way of doing that, the easiest way, is to just increase the temperature if you can. Right? So we see here in every case we have a low temperature and a higher temperature, and we have a huge temperature difference. Right? So, you know, for this case of iron, or maybe we'll jump down, we'll look at the diffusion of carbon in ferrite. If we increase the temperature of our material from 500 to 900, right, we see about 2 orders of magnitude, 100 times faster increase in the diffusion rate. So, you know, looking at these trends is all well and good if we have these numbers, right? If we have the activation energy, if we have the pre-exponential factor D naught, we can, you know, make these conclusions. But how do we get those numbers? And the answer to that is through experimentation. So if you take this expression here for D, right, you can manipulate that into a point slope formula to draw a line, right? So if I take the natural log of D, take the natural log of both sides, right, I get the natural log of D, the natural log of D naught. The natural log cancels the exponential, and so then I have this term here by itself. And if I look at this carefully, I can say, okay, so this looks like this is a constant. Here's another constant. And then if I look at my x variable as being 1 over t, then I have this point slope form for my expression. And this is very convenient for plotting data, right? So if I take a series of experiments, right, where I take these various materials and I diffuse in these impurity atoms at controlled temperatures, and then I measure, okay, what is the concentration profile, right? And I back up to figure out what the diffusivity must have been, right, to create a certain concentration profile after a certain time, right? Then I can plot my temperature and my diffusivity, or my 1 over temperature, my reciprocal temperature and diffusivity, right? And I will get a line. If I plot, well, the log of the diffusivity versus the reciprocal temperature. And if I fit an equation to that line, the y-intercept gives me my D naught, right? And my slope gives me my activation energy, right? So you can do a bunch of experiments, figure out these lines, and then extract what your different diffusion parameters are. Okay, so lastly, we'll look at an example of non-steady state diffusion. And in this example, we are going to be looking at carburization of a steel part. So we're diffusing carbon into steel at an elevated temperature to harden it. And in this case, right, this is a non-steady state diffusion where we have a constant concentration at the surface, right, and a thick enough part that we can consider it to be semi-infinite, right? We're never going to diffuse all the way into the interior. And so now we can use the expression that we had earlier in the notes that applies to this scenario. And we are asked for the time. How long will it take to achieve a carbon content of a certain percentage at a certain position below the surface, right? So we're looking for C sub x to be a certain value at a certain percentage, and what we want to know is the time. So the time is our unknown, and we can plug in everything else, right? We're given the initial concentration, we're given the surface concentration, our desired concentration, and our desired depth, and we can take the concentration, or the temperature, and consider the scenario that we're talking about, which would be carbon in iron. So we're going to pull the D0 value, the activation energy, and then the temperature that we had in Kelvin to calculate this diffusivity value, right? So this is already accounting for our diffusion scenario and our temperature. Give us that number. And then it's just a matter of plug and chug. So we plug in our concentrations, and we calculate, right, a value that is this corresponds to this error function. And here's where that table comes into account. And we look in that table, right, for the two values that bracket on either side that are our value that our error function is equal to. And we can use that table to interpolate and kind of undo the error function to figure out, okay, if my error function of this inside portion equals this number, what is this actually equal to, right? That would be our z function here. And so in the table we can see that, okay, if our error function of z is 0.421, that's between, right, these two values here, which correspond to z values 0.35 and 0.4. And here's just a matter of interpolating, where we say, okay, if this number here is a certain percentage up from this lower bounds or down from this upper bounds, then the z here must be the same percentage relative to those bounds. And we can figure out through interpolation what that z value must be, and then it's just a matter of solving for t. And so we see here that the carburization in this problem will require 7.1 hours to complete. Now we could increase that time or decrease the time, right? Most easily by changing the temperature, because the temperature would change this diffusivity. Higher temperatures would make it greater, lower temperatures would increase it. So that gives us the easiest way of affecting this time necessary for diffusion. And this will come into play in both this example here, where we're carburizing steel, and much later, the second half of this course, where we are introducing impurity atoms, right? So diffusion and these temperature-driven is a temperature-driven phenomenon. That is one of the primary ways that we can change our material properties.